All right, so we're going to start the presentation back up, and we're going to talk about one of uh, the most common processes that gets modeled, and that is just the decision-making process. So this is something that is a little bit, we talk about it in both the vector and the raster class, but these include problems like where do I put something, or where should I expect to see something. So those are basically decision-based models. And typically, these are best answered through using a multi-criteria evaluation, which you should have read a little bit about in some of the readings. So we're looking at finding out areas that are either capable or suitable of supporting an activity. And sometimes we're interested in finding the degree of suitability or capability. So some things may be more suitable or less suitable, but sometimes maybe in between. And oftentimes it becomes a little bit of a human process to actually determine overall where something should happen or should be based on these capability or suitability models. Okay, so we do this a lot. It's actually the fundamental way to model resource management in GIS, and does form the structure for many biophysical process models. So we might use it for finding out potential habitat for a certain creature, or finding out, where we would want to restore certain things to be back to the way they originally were, or set aside certain areas. So these concepts are the same for both raster and vector, but how they're actually implemented is different. Okay. Capability and suitability, I'm using them almost interchangeably at this point, but capability is technically the physical potential of land unit to support activity, where suitability can be social or economic, and it's the potential of a land unit to support an activity, and it can even be an economic activity. Now, raster data lends itself a little bit more to the natural world, I would say, and so oftentimes we're talking more about capability when we're talking about these types of models in raster GIS. However, there is the interplay a lot of times between capability and suitability, kind of like what we're going to do in the lab today. In other words, what would be a great place to put a nature preserve based on a capability and a suitability model. Another type of model may just be classification. We may just be interested in finding what areas match a certain set of criteria that would fall into a certain class. And that's not really mutually exclusive to capability or suitability. It overlaps a lot with suitability. We might be just trying to find areas that would be suitable for X and suitable for Y and suitable for Z. That would be a classification model. In fact, the creation of the land cover data set itself, you could think of as a classification exercise. You might start with a multi-band image and say, okay, well, if the reflectance is really high in the green and the near infrared, then it's vegetation. If not, it's not vegetation. Yes, that would be an example of doing classification. So there's some terms associated with doing this type of operation. The first being a factor. A factor is the category of information that we use to define the limiting criteria. In our case, factors are the raster data set layers. So elevation might be a factor in making a certain decision, or land cover might be a factor in making a certain decision. or distance from something else might be a certain factor in making a decision. So all of those things might be factors in making our decision. So those are all raster layers. Okay. A constraint is a numerical value that we can think of as a formula that we apply to the factor in order to get a resulting raster data set that shows us whether or not something is capable or suitability. It's a threshold that must be met for acceptability. So oftentimes in the raster data model, a constraint is implemented through a greater than or equal to or less than. It creates a Boolean operation, a 0 and a 1, or no data and a 1. A rating is similar to a constraint, but it's a mathematical operation that yields a gradation of values. This area is really good, it's really suitable, this area is less suitable, this area is even less suitable, this area is the lowest suitable or capable. So rating is usually implemented as a series of mathematical formulas or a function that produces a series of values. And you'll see this in the lab today. We'll use values that produce a series of values. So a rating schedule is a table of ratings for different characteristics of a factor. So sometimes we'll have different factors and we'll have a value that represents how much different values for a factor. And then the raw values for the factor won't actually indicate how suitable it is, but the ratings values are ways to transform the raw factor values into the level of suitability. So in this case, it's a mathematical operation. So how would we actually implement this in a raster GIS? So let's say we had slope. We can actually calculate. So we haven't talked about slope or what it is or how it gets calculated, but we will. But it is a tool that just comes with ArcGIS. We have this slope operation. We have our elevation data set. Okay. I'm just going to run it with all the defaults there, which is a dangerous thing to do actually, but so there's slope. What's that? We don't have a what?
Our big screen is not showing anything.
Oh, I'm so sorry. Thank you for letting me know.
It showed up and then disappeared. Got it.
We need to put a work order in for, you need to get some proper blinds in that room. It's pretty washed out, eh?
Yeah.
Oh, the lights are on? Oh. Anyway. That does look a little bit better, but in the front, I couldn't get the blinds to go down all the way. Is that still a problem, or you get them on that? You get them down all the way?
Got them. We got a 4.
Okay.
Rated a 5.
Oh, 4 out of 5. You got them further down than I did, but not that far down. Oh, not all the way down. Okay.
I would go 10.
Oh, a 4 out of 10.
Yeah.
Okay, that's not very good. Okay, so this is a slope map that I just created. I just ran the slope tool. So the high values represent high slopes. And this is slope in degrees. So, a 90-degree slope is like falling off a cliff, right? Which actually isn't possible. We'll get into why, but you actually can't get to 90. in a digital elevation model like this. But this data set represents slope. So the value in every cell is the slope of that cell. So if I was to implement this factor score, basically what I want is, if this is true, I want the values to be 10. If this is true, I want the values to be 5. If this is true, I want the values to be 0. Okay? So how can I do that? Well, there actually are a number of ways to do that in ArcGIS. One of the simplest ways is to just run a tool that is called, reclassify. Exactly. Reclassify will allow me to do that. So I'm going to put the slope over here. I'm going to use the value as the reclassify. And notice by default I get all these values. I don't want all those values. I only want these 3 values, 1, 2, and 3. So I have to hit this classify button, and I have to lower this to 3 classes. Now I have 3 classes. Okay. These are the output values that they're going to get, and these are the input ranges. So if I wanted to change these values, I could say 0 to 10 is going to get the value what? What does it say? 10. And 11 to 20, I should always have it be inclusive. So I should actually go 10 to 20. If I had an integer data set, it would be fine to use 11. So I was assuming an integer data set here. And then if it's over 20, I want it to be a value of 3. Or sorry, no, it's not 3. 10, 5, and 0. So now I have changed it so that, or when I press go, I'll change it. If I wanted to be really comfortable, I could change this to 90. But by default, it should put the highest value in that range. So now I can run this reclassify tool, and I will get values that show me the areas as those 3 values, 0, 5, and 10. So what do the values here, 0, represent? According to this table. Yeah, they're the areas where it's green, but what slopes? The 0. Yep, exactly. It's over 21. My factors are more to do with how capable it is for a certain activity. This might represent like areas that I want to build on. Do I want to build on anything higher than a 21-degree slope? So what I'm saying is those are totally unsuitable. All these light green areas are totally unsuitable for building on. Whereas the blue values have a moderate slope, and so they're somewhat good for building on. The 10 is the most suitable, and it has the lowest slope. So the rating doesn't have to match the factor score. I mean, sorry, the factor value. We went the opposite direction. We could have, so that's creating like hard breaks. Okay, we could have decided, we could have done something like, could have gone to map algebra. I'm not spelling algebra right. Raster calculator. There it is. It's called raster calculator. It used to be called map algebra a long time ago. Okay, we could have said, okay, well, the slope is how could we say if it's really small? Well, we could do something like this. The slope 90 minus the slope is the factor score. In other words, what would that do? Well, in areas where the slope is 0, are we going to get a big number or a small number? Yeah. So it's going to be really suitable. Right? So it would be really suitable if we did that. If we wanted to keep it on a same 10 to 0 scale, we could do something like this. Right? We could do slope divided by 9. I'm going to say 9.0. So this will do, and then minus it by. I'm going to say by 10 minus. Watch this. This will be. The highest value was actually like 83 or something. I forgot exactly. 83 divided by 10 is 8.3. So now, the highest value here that we can get, so if this is 83, then we'll divide that by 8.3 and we'll get 10. So the highest value we can get is 10 there. Because if this is 5 divided by 8.3, if this is 50 divided by 8.3 is going to be a smaller number. So we're always going to get a number between 0 and 10. So I basically was thinking about what the math is to keep it on that same scale. If I hit run here, I'm going to get a similar factor score that ranges from 0 to 10. But now, that's it. Now, 10 still represents the areas that are most suitable. They're the flattest areas. And these are not suitable. This is the way you get to the beach. Drive down this canyon and pop out. So that's why it's so steep right there. Okay, so those are just two different ways of coming up with a very similar factor score range, but this one is a gradation and this one is stepped. And there might be different reasons. You know, it all depends on what the end user wants. It might be just as expensive in real life to do, you know, whatever the ranges were, 0 to 10. Or maybe it isn't. Maybe it isn't. Maybe it is a little bit cheaper, the different slope capabilities. Sometimes it stops. Okay, so that's the way we use a rating schedule. And a rating schedule can be a table or it can be a fixed formula. But in either case, it needs to be something we can implement mathematically to create. All right, so there are three different ways that we can implement a capability suitability model. One is just through pass-fail screening. And in raster GIS, pass-fail screening just means that we either do a big AND operation, this and this and this and this all need to be true, or we do a big multiplication problem. Okay? So that's how it's implemented in a raster GIS solution. Every factor we come up with is either it's suitable or it's not suitable. So we come up with a bunch of suitable, not suitable. You know, it has to be this high in elevation, and it has to be this land cover type, and it has to cost this much or less. We come up with a bunch of criteria, and then we create the proper criteria maps, and we multiply them all together, or just say this and this and this and this. Okay. So here's an example of a factor constraint. Might be the number of frost-free days has to be greater than 146. All right, an ordinal combination is the second way this works. An ordinal combination creates multiple values in each output layer. Okay? The next two are actually both going to create multiple values in each output table. But what you can do is basically combine them in a few different ways. So let's say we have the output from slope. We also have the output from, the land cover suitability. Well, then we can combine them by some mathematical function. And doing some mathematical function is actually pretty easy in ArcGIS. There is a tool for doing some mathematical function. It's called cell statistics, and it's still a local operation. I know it's called cell statistics. Cell statistics, there it is. So cell statistics, what it does is it allows us to compute through multiple data sets, 10, 5, 2, 18, 40 different data sets, and specify a mathematical function of how to combine them. So let's say we had several different factors. We only have one factor over here. Let me get another factor in there. So let's say slope has to be a certain amount, and let's do another reclassify here real quick. I'm going to reclassify land cover. Number of classes. I'm going to do just 3 classes. Do 4 classes. 4. Okay. What I'm going to do is say if it's developed, which is, well, I should look at the table here. What are developed? Developed are 1, 2, 3, or 4. So in other words, if it's 1, 2, 4, then it's not suitable for development because it's already developed. If it's crops, grassland, deciduous forest, if it's crops or grassland, which would be 5 or 6, I'm going to say it's kind of suitable. No, sorry, it's really suitable because there's no trees to clear. If it's a forest, which is, what are the forested values? 7 and 8. 7 and 8. If it's a forest, those are only somewhat suitable because I have to clear trees, and in Laguna Beach, people are going to be upset if I have to clear trees. And then finally, actually, I'm going to include scrub shrub in that. Oh, mixed forest and scrub shrub. So I'm going to go all the way up to 12. And then anything above 12, 13 and up. See how now that it's in an integer data set, I don't go 7 to 12 and then 12 to whatever. You only do that if it's, because if I included 12 here, it'd be ambiguous. But you do include the breaks if it's floating. Otherwise, you'll miss. Like if it was floating point and you said 12 and then you started with 13, everything between 12 and 13 would get no data. All right, so 12 to 99, I don't know what this is. That's also unsuitable. I can't build inside of a wetland. Okay. So run this guy. So now I have my land cover suitability. So really I've got 0, 5, and 10. Those are my land cover suitabilities. So if I wanted to combine, I'm going to use this first slope suitability. So I wanted to combine my slope suitability with my land cover suitability. If you only have 2 data sets, you might as well just run the tool. Okay. Well, let's say you had 5 or 10 different data sets. What I'm saying is you might as well just run the add tool for sum, or well, actually there isn't a min tool. So what I'm trying to get at is this cell statistics operator right here allows you to input as many data sets as you want. So I'm going to put my reclass data set of land cover and my reclass data set of slope. And then I can choose from all of these different options. I can choose the mean. So what's that going to do? What's mean? What does mean mean? The average. So it's going to give me the average suitability value. So that's what I might be interested in. Okay? Or it might give me the majority value. That's kind of probably a little bit more abstract. Anybody got a guess at what that might mean? Right, so it's the most often repeated value. So kind of like it would be I get another word for that in statistical terms would be the mode, the most often repeated value. Here, that's going to produce a lot of no datas because sometimes there's only 2 data and they're different. Okay. So, but that might be an interesting thing if there were like 100 data sets and you wanted to know what the most often repeated suitability value was. The maximum and the minimum are both important sometimes because sometimes the way how suitable it is just dependent on the very minimum suitability. So it's like a filter. Which one is producing the most minimum suitability? And I know that's the one that actually means how suitable it is in my particular application. Right? And then I guess maximum would be used less frequently, but can still be used. The maximum suitability value. Yeah. I mean, I could see somewhere where that might be the case. Like if I had a bunch of things that represented different things that people enjoy doing, different layers that people enjoy doing, and it didn't matter if they had all of them. It just mattered if they had any of them. They would be satisfied. Then maximum might be the way to go. Median is the middle value, which also, if we only have 2 data sets, is not going to be important. But if we had lots of different data sets, median is the value right in the middle. Minority is the least often chosen value. So again, probably not that often. Range is a measure of spread, as is standard deviation. Standard deviation is the average distance from the mean. Well, it's not exactly that, but you can think of it like that. And then range is just the minimum maximum difference. Sum is another one that would be used pretty often. So let's choose sum here. Sum would be the addition of the values, all the values through. And then finally, variety is how many unique values there are, which again, probably for this particular application wouldn't be very common, but that might be important in some other statistical operation. Okay, so we got the sum. We'll go ahead and close this land cover data set. So if I run this, the output of every cell is going to be the sum of both of the other cells. So in this case, first of all, I'm trying to show suitability. Is this an appropriate color scheme for suitability? What should I do? What kind of color scheme should I choose? Yeah, I want to choose either a stretch or a classify because I want them to change values slowly. Choose classify, and then yeah, like green to red might be good, like this. So in this case, is green the most suitable, or is red the most suitable? Red is the most suitable, and if I might want to change that. I think there used to be a way to flip them in ArcMap. Anybody know how to do that in Arc? It's just already flipped for you? This one? Or this one? Red to green. Not quite the same color green. But yeah. Oh, there's a reverse ordering right there. I like this darker green a little bit better. So options, we're going to reverse ordering. And the green areas are now the most suitable areas for development. So they're basically the flattest. They score high in being flat, and they score high in being the appropriate land cover, like already open land. So they're not already developed. The red areas are the lowest. They're probably already developed, or they're wetlands, and they're steep, already developed areas. So this map I might present to City Council, and we could maybe start a dialogue about where we wanted to put stuff. I could insert a sorry. When I go to map, I could add a. I thought there was a way to add a base map that didn't cover the background. There was in ARC map. I just want the labels as a separate layer. What if I go imagery with labels? Nope. That doesn't really work. Okay. I might have to get a layer that just overlays like the roads is what I'd want to do, so that I get that. But I could still use this to start a dialogue, and maybe I could find out what's in this area. In this city, there's probably not any realistically areas to develop. But let's see what's under there. But that's not going to be the case with every city. Okay, so that's the high school. Right. So I don't know why. Let's see what it shows up in land cover as. Where is that layer slope? Okay. So that shows up. A lot of it shows up as. That's developed open space. This shows up as developed low. Reclass land cover. So those are both 5. No, that's a 10 area. 10 represented open. Oh, because I said open space I should probably take that developed open space out. Because if it's developed open space, we probably can't really develop it. Unless maybe it was a park or something. But a high school is not going to be able to be developed over. But there might be other areas. Let's see what this is. That still says developed over space. That actually doesn't look like it's really developed over space. So we probably could develop that area if we wanted to. So it's flat and it doesn't have any houses right now. But we want to refine our model. But that's just a suggestion, or sorry, just an example of running that particular model, like a model like this. And you can see we could do it on a much larger scale. So this is just looking at the suitability of a certain plant to grow. It needs these 2 different criteria. And we'd probably do this on a bigger scale, and we'll actually have a lab similar to this later. Okay, so here we have the minimum. Here we have the sum. So that's an appropriate value for summing all. We call that the addition of factors when we sum it. We call it graduating screening when we get the minimum value. And then finally, we could have a weighted linear combination where we decide, okay, well, maybe we decide that land cover is actually twice as important as the slope. Well, if that was the case, if land cover was only twice as much as the slope, we could first multiply land cover values by 2 and then add them together. So we would call that 2 value the weight. So if we came up with a weight for each of the different factors, we multiply it by the weight and then add them all up. We'll practice this a little bit in the lab, so I won't demonstrate that right now. But the ultimate goal here is to think about these processes as a series of overlay problems, or a series of raster calculator problems, something like this. Okay, this is a vector example, and it's actually taken from the 217 book. But we're going to do it as a raster model today. So here's an example that's also taken from the 217 book that you could read through. I'm going to go ahead and stop there and then get into the laboratory assignment. Let's see. That's all. This is all good advice, but that's important. Okay. Minimize that. And now I think I'm going to break the video right here, just because we transitioned into the lab, even though this will be a